And today I'm going to share with you a very interesting topic regarding water flood. And the title of my presentation is Reservoir Engineering Aspects of Water Flooding. This is the outline that we will learn today. First, I will introduce what water flood is, and then I'm going to share with you water flood pattern. We will learn about displacement efficiency, areal sweep efficiency, vertical sweep efficiency, and lastly, surveillance and diagnostic plots to analyze water flood performance. Let's start with introduction. So there are, of course, a lot of activities that we can do to boost oil production. Of course, we can do exploration, enhance oil recovery, and then infill drilling, artificial lift installation, work over by doing zone transfer, and then production optimization, stimulation. Many things we can do to improve, to enhance, to boost our oil production. But among all these activities, water flood and water flood optimization is considered the most mature, the most effective way for us to enhance oil recovery. All right. Of course, exploration can be very expensive, and enhanced oil recovery also, it can be very expensive and challenging as well. A lot of uncertainties there. Okay, but water flood, it's quite mature, it's very effective, and that's why it's very important for us to understand it better. So what actually water flood is? Water flood is a secondary oil recovery method. We do this by injecting water through injectors into our reservoir to sweep, to displace, to push the oil into the producers. Right? That's very simple. And the main objectives are at least these two factors: to provide pressure maintenance, to increase our reservoir pressure and to keep our reservoir pressure, and also to improve the sweep. And these two things will result in, of course, oil recovery enhancement. All right, so there are a lot of things that waterflood can do to our operation, but the most important things are pressure maintenance, also sweep improvement to obtain oil recovery that is enhanced. And this is the illustration that, of course, we will start by primary recovery, and then we will increase our production. We will prolong our production life by doing secondary recovery, and we can do also tertiary recovery or enhanced oil recovery. If we do only primary recovery by natural flow, we can only achieve like these factors, like this drive mechanism, rock and fluid expansion. Of course, it will give us the lowest recovery factor, and solution gas draft also is not very big. The recovery factor, yeah, it can give you 35 through 75%. And water flood will give you this high recovery factor. So water drive and water flood is actually quite the same to give us the recovery factor. All right, so by having water flood, we can improve our recovery factor to achieve this level. All right. And of course, one of the things that is very important regarding water flood is how we calculate the recovery factor. The recovery factor can be calculated using this formula. So it is the displacement efficiency multiplied by areal sweep efficiency and by vertical sweep efficiency. This is how we calculate the recovery factor provided by the water flood or the water injection. And to calculate the cumulative production that we can recover from water flood, this is the simple formula to calculate it. So NP is cumulative oil produced after the water flood, and S is the initial oil in place at the start of the water flood, and of course displacement efficiency, areal sweep efficiency, and vertical sweep efficiency. So we need to actually calculate or estimate the displacement efficiency, areal sweep efficiency, and of course vertical sweep efficiency. And these are the things that we will learn in this presentation. But before we go to that particular subject, we will first learn about water flood pattern. There are three big categories of pattern for water flood or water injection. You can name it also that way. It is peripheral injection, regular pattern, and irregular pattern. And you can see this pattern, peripheral. It means that you will set your injectors at the periphery of your reservoir. Regular, it means that you will create a lot of pattern regularly. And irregular, it is quite random. It is not governed by any pattern whatsoever. It is irregular. And first, we will talk about peripheral water injection or peripheral water flood. This is the setup for the peripheral water flood. The good things about this pattern is that it will delay your water production or delay your water breakthrough. It will lower your water production. Why? Because the distance from the injectors to the producers is quite long, right? So water need more time to arrive at our producer. So it means that you will get lower water production for some time. It will delay your water breakthrough. But the drawback is slower fill up and pressurization, right? It's quite slow because the water will need more time to arrive at this produced zone area. And then it will delay the field response to flood. And of course, injectors must face a high local pressure, which result in lower injection rate, right? Because between them, around them, everything is water only. And it will give a high local pressure, which will result in lower injection rate ultimately. And it is good if you want to implement peripheral water flood. It is good for high permeability reservoir. Why? Because it allows the water to arrive at this produced zone faster because we have higher permeability, right? And it is also good for operations where water production is strongly undesirable. So if you really don't want water production, then you can set up your water flood with this pattern, peripheral, because you will have delayed water breakthrough. All right, and what about the regular pattern? Of course, by this configuration, we will have faster fill up and faster pressurization, which is good. It will result in faster field response to flood because the faster fill up and faster pressurization, and it will usually result in higher sweep efficiency compared to that of irregular or peripheral water flood. But indeed, you will need high investment. You will drill a lot of wells, a lot of injectors, right? And you will need to do conversion job to convert your producers into injectors in order to create a lot of patterns, a lot of regular patterns like this one. And risk of early water breakthrough and water recycling can be high if your spacing is too high, is too tight. The distance between the producer and the ejector is too close. And of course, it will increase your risk of water breakthrough and water recycling. It is good. It is recommended for large reservoir because in large reservoir, if you set up your water flood with peripheral water flood, it will take too long for the water to arrive at your producers, right? So if you have a large reservoir, you need to set up your water flood at this pattern. And also it is good for you to use this pattern in homogeneous reservoir and reservoir with a large well stock, of course, so that you can do conversion job to convert producers into injectors or injectors into producers if you have large well stock. But lastly, we also can do irregular pattern water flood. It is more selective. It is focused. Whenever you need or wherever you need pressurization, you can you can convert your producers into injectors there. You can drill your injectors there. So it's selective, it's focused, it will give you faster field up and pressurization at each area that needs water flood the most. All right. And then faster areal response to flood. Not overall, but only areal. Okay. And usually it will less costly because yeah, like this one. We only need few injectors in this example, in this illustration. Okay, but of course, overall, if we talk about overall, it will give us slower fill up and pressurization. It will slower the overall field response to flood. And actually, it will give us more difficulty to track oil movement and to identify bypass oil zones. Okay, but it is very good. It is recommended if you have small or marginal fields. Okay, if you have small and marginal field, you cannot do regular pattern water flood. It will be too costly. You will need to drill a lot of wells just for a small or a marginal reservoir, right? So in this case, you need to do irregular water flood. And of course, if you have limited number of wells, and if you have severe heterogeneity, compartmentalization, a lot of faults here and there, fractures, in that way you cannot do pattern water flood. It will be very challenging, but it is better if you set your water flood to be at this irregular pattern. All right, so far so good. And of course, we are interested with regular pattern water flood. There are a lot of patterns: normal 9 spot, normal 7 spot, normal 5 spot. We call it normal if we have injectors surrounding the producer. All right, and we also have this configuration: direct line drive and staggered line drive. And we can do also inverse pattern. Inverse 9 spot, it means that injector is surrounded by producers. Okay, inverse 7 spot, inverse 5 spot, direct line drive, and staggered line drive. Let's talk about them one by one. First, normal 9 spot. Okay, there are 9 wells: 1, 2, 3, 4, 5, 6, 7, 8, 8 injectors, and 1 producer. But ultimately, you need to calculate it this way. We only have 3 injectors actually. Why? Because we need to calculate this way. We have 4 injectors with half of this sphere, right? One, this injector, this injector, this injector, this injector only give you half of the cumulative product, cumulative injection. Okay, for this particular pattern. And 4 will give you a quarter of the cumulative injection, represented by this, a quarter of a circle, or this one, or circle. Okay, so ultimately it will give you 4 times half and 4 times a quarter, 3. So it is 3 injectors with only 1 producer. Of course, it will give you high injector to producer ratio, which ultimately will give you fast pressurization and high sweep. Okay, so for normal 9 spot, it's good. Okay, and if you do inverse 9 spot, it will turn to be the other way around. 1 injector only versus 3 producers, which of course will give you relatively slower sweep and pressurization as opposed to that of normal 9 spot. And then, but the good thing about inverse 9 spot is that it can be downspaced to either 5 spot pattern and also direct line drive. Okay, in what way? In this one. Okay, we go from inverse 9 spot to 5 spot pattern. Okay, you can see this one, this highlight. And in this particular pattern, we will have 1 versus 1. 1 injector versus 1 producer actually. And of course, with 1 by 1, it will give you more efficient performance compared to inverse 9 spot. And inverse 9 spot can also be downspace to direct line drives, right? You just need to convert some injectors into producers or producers into injectors. And this way you will have direct line drive, which also will give you 1 by 1, 1 injector and 1 producer. It will give you more efficiency compared to that of inverse 9 spot. And it is actually more useful in reservoir with directional permeability. If you have fractures, if you have heterogeneity, all right. And We can also set up our water flood to be, sorry, okay, it is interrupted, to be in first 7 spot, 1 injector, 2 producers, okay, and then slower, and of course it will give you relatively slow sweep efficiency, slower sweep and slower pressurization. Subham, can you still hear me?
Yes, sir, you are perfectly
Okay,
audible.
okay, thank you so much. And we can also do normal 7 spot, all right, and of course it will give us 2 injectors with 1 producer ultimately. How can we get these 2 injectors? It's easy. Okay, 6 times 1/3 equals to 2. So it will give us 2 by 1 higher injector compared to compared to the producer. So it will give us fast sweep and fast pressurization. And normal 7 spot can also be down space to be 4 spot pattern in this way. All right, so you just need to add more wells. You need to do infill drilling, okay, as well as well conversion. Okay, so you need to drill your well here, here to get these producers here. Okay, and you need to convert your producer at this center area to be injector. In that way, you will have normal 4 spot. Again, it will give you 1 by 1, 1 injector versus 1 producer. It will give you tighter spacing, right? And usually tight well spacing can give us higher recovery because we drain all areas of our reservoir. And also it is good for heterogeneous and tight reservoir. All right, so far so good. And yeah, that's all about waterflood pattern. And now we are ready to discuss about displacement efficiency, and it's quite challenging. Okay, displacement efficiency is defined as the fraction of the movable oil that has been recovered from the swept zone at any given time. Okay, you can see displacement efficiency microscopically or macroscopically. Okay, in this presentation, I'm concentrating on macroscopic displacement efficiency. All right, this is the formula. Displacement efficiency is volume of oil at the start of the water flood subtracted by remaining oil volume divided by volume of oil at start of our water flood. Okay, numerically it can be calculated this way or this way. And it's easy actually. Initial water saturation, initial gas saturation can be analyzed core analysis or using log analysis. But the big question is, how can we estimate this one? This average water saturation. It's not that easy. It cannot be analyzed by log analysis. Okay, you need to do reservoir simulation to actually calculate your average water saturation. And of course, reservoir simulation, it's not that easy. It's challenging. Okay, so in this particular presentation, I'm going to share with you uh, a simple way, a relatively simple way to estimate the water saturation average. We start by fractional flow. This is the setup. This is the configuration of our system, and it will give us this equation. Okay, it's quite complex, but no, it's actually quite uh, it's easy. Okay, provided that we have all the data, the permeability, the relative permeability, the area of our reservoir, okay, or the cross section of our reservoir path, the viscosity, injection rate, and so on and so forth. It's actually easy. Okay, and you need to also see this one, alpha. This is the tiltness of our reservoir. Okay, and if we assume a horizontal reservoir, it means sin alpha will be 0, and it will give us this simple equation. So FW is fractional flow, or it is actually water cut, right? You are familiar with water cut. Fractional flow or water cut can be calculated using this one. Okay, just just to remind you, we actually want to arrive at this parameter. Okay, how can we actually get this average water saturation? And this is the story. We start by defining our fractional flow. Okay, and fractional flow, using this one, we have also our relative permeability plot. Okay, oil relative permeability and water relative permeability curve, which will be plotted against water saturation. And of course, you can see we start from FW, from fractional flow. We have this curve if we do core analysis, right? And it will give us, lastly, this correlation or this relationship, which will correlate FW with water saturation. So now you can get the sense. You can estimate your water saturation by knowing first your water cut or your fractional flow. All right, this is the conclusion. So FW, you go to relative permeability or mobility ratio, and it will give you your water saturation. But that's not the end of the story. Okay, we need to actually uh, calculate this one. And this is the how we can actually get the true relationship. We start from this one. So relative permeability ratio can be represented or can be estimated using this correlation. So A times exponential of minus B times SW. You can make a logarithmic calculation, okay, to obtain this linear relationship. And the good news is that in this interval, in this water saturation interval, we can actually get a linear trend. And that's good because we love a linear relationship. It's easy to estimate. It is easy to construct a linear correlation. Okay. And this is the correlation. So if you have your data, okay, you have your laboratory data, your relative permeability information against the water saturation, you can actually calculate your A and B. Okay. If you have A and B, finally, you can estimate your water saturation. And you will get this type of curve, fractional flow, water cut against your water saturation, which will give us insight how to actually obtain this average water saturation. Okay, but again, that's not the end of the story. Okay, first we need to do, after fractional flow analysis, we need to continue with frontal advance analysis. At water breakthrough time, you will have this saturation profile. Okay, at a time of our water breakthrough, the front will have saturation of SWF, water front saturation. Okay, and the average water saturation at water breakthrough time is called this one, average water saturation at breakthrough. Okay, so we can now get a sense of a reservoir, of a average saturation of the reservoir. Okay, please remember, we are talking about average reservoir saturation. And after breakthrough, of course, we will have higher water saturation. In this in this case, it is called SW2. Okay, at SW2, you will arrive at this water saturation called SW2 at this producer. But in average, you will have this one, SW2 bar, average water saturation at time 2 after water breakthrough. Okay, and this is the schematic, but actually we can estimate it or we can calculate it using this approach. So we construct our fractional flow curve starting from Conat water saturation or initial water saturation. We draw a tangent line. Okay, we draw a linear tangent line to touch this curve here in this particular spot, and we will have our water cut at the front, as well as the saturation, water saturation at the front of our water flood. Okay, and if we extend the linear trend until this one, we will have average water saturation in breakthrough time. Okay, and then we continue our water flood, we continue our production, we will have water cut 2 after water breakthrough. Okay, so at any given time after water breakthrough, you can do water sampling from your producer. You will do processing in your laboratory and you measure the water cut. Okay, if you get that water cut, you can estimate the average water saturation in your reservoir. Okay, after you get your water cut, you draw your line here to get this one, water saturation after breakthrough, and the average water saturation in your reservoir throughout your reservoir is actually this one. Okay, SW2 bar, average water saturation after your water breakthrough. So it means we can get finally water saturation, water fractional flow or water cut to give us water saturation. Okay, using this plot or numerically, you can also calculate it this way. Okay, so finally, you know the average water saturation within your reservoir. Okay, so it means that now you can calculate your displacement efficiency. And also displacement efficiency is influenced by mobility ratio. If you have mobility ratio below 1, you will have like this one, piston-like displacement, which means oil moves faster than water. And whenever your oil moves faster than the water, it will give us piston-like displacement. Okay, and again, water mobility ratio is defined by this formula, the mobility of our displacing fluid, in this case water, divided by the mobility, relative permeability divided by viscosity. Okay, that's mobility divided by the mobility of our oil, which is the displaced fluid. Okay, so if you have mobility ratio below 1, it is good thing. You will have piston-like displacement. Your oil moves faster than water. But if you have mobility ratio higher than 1, you will have like this one. Okay, you will suffer in displacement efficiency. You will have fingering and channeling where water moves faster than your oil. And of course, it will make a lot of bypassed oil zones. Okay, so finally, for displacement efficiency subject, you do water flood. This is what you will have in your reservoir. And at your producer, you take your sample and then you measure your water cut. You get the water cut information. You do the fractional flow analysis, frontal advanced analysis, and you will get your average water saturation within within your reservoir. And finally, you can estimate your displacement efficiency. Okay, so we need to suffer painful approach, but that's okay, just to get this average water saturation. But actually, it's really it's really a blessing if you can actually estimate your average water saturation, because otherwise you need to do reservoir simulation just to get this number. Okay, and also displacement efficiency is also influenced by viscosity in addition to mobility ratio. Like this one, you can see we start from low viscosity oil to high viscosity oil. Of course, if you have high viscosity oil, you will get higher water cut faster, and it's not good thing for us. Okay, like this one, you will have high water cut faster compared to that of if you have low oil viscosity. Okay, that's one thing. The oil viscosity influence our fractional flow, influence ultimately our displacement efficiency. And of course, the effect of reservoir depth, there is effect of our reservoir depth to our displacement efficiency. If we have, yeah, starting from this correlation from fractional flow analysis, we can do up-dip injection where our injector is located higher than our production well. And we can also do down-dip injection where our injector located at down-dip side to our producer. Okay, if you plot the fractional flow curve, you will get more or less this trend. If you have no dip, horizontal reservoir, you will get this green trend, green profile. If you have up dip injection, okay, injection well located up dip, you will have faster, higher water cut, and it's not good. But if you locate your injection well uh, lower than your producer, you will have better performance. Okay, so you can see in this plot, in this chart. Okay, so actually in this part, we want to know how to calculate our displacement efficiency, and we want to know which factors finally will influence our displacement efficiency. Okay, but that's one thing. Displacement efficiency is just one thing. The other thing we need to estimate is our areal sweep efficiency. It's also very important. Okay, the areal sweep efficiency is defined as the fraction of the total flood pattern that is contacted by the displacing fluid. Okay, there are a lot of factors influencing areal sweep efficiency. Again, mobility ratio, flood pattern, cumulative water injected, or also reservoir pressure distribution between injectors and producers, also our directional permeability and heterogeneity. Okay, and this is the representation of how areal sweep efficiency can really influence our water flood performance. If you have like this one, it means that you have your water flood giving you high sweep efficiency. Okay, your water sweeps the reservoir well. Okay, it's quite uniform. But if you have poor sweep efficiency due to mobility ratio, due to heterogeneity, due to uh, reservoir pressure, which is not uh, equalized. I'm sorry, it is interrupted again. Okay, you will get this profile. A lot of bypassed oil there caused by this poor sweep efficiency. Okay, so it is really different, the performance between high sweep efficiency and the poor sweep efficiency. And of course, we need to calculate or estimate the areal sweep efficiency. And for what before water breakthrough and after water breakthrough, the calculation is easy. Okay, compared to displacement efficiency estimation, it's quite easy. Like this one, before water breakthrough, you can estimate areal sweep efficiency in this with this formula. So it is cumulative water injected divided by pore volume multiplied by this average water saturation at water breakthrough minus initial water saturation. And after water breakthrough, you can use this formula. Okay, so you need to calculate first areal sweep efficiency at water breakthrough, and then you also need to calculate this one, cumulative water injection and cumulative water injected at breakthrough time. Okay, that's simple, the formula. But of course, we need also to calculate areal sweep efficiency at breakthrough time. Okay, you can use this plot to estimate the sweep efficiency at breakthrough time, or you can also use this formula. It's quite easy as well. So you just need to first estimate the mobility ratio, and after that you can apply this calculation to finally arrive at your areal sweep efficiency. All right, so that's easy. Actually, numerically, it is easier than that of displacement efficiency calculation. And it is also provided this correlation. Okay, so if you have reciprocal mobility ratio 1 by m, and if you also know your water cut, you can actually calculate or estimate your sweep efficiency using this plot or using this formula. Okay, it's quite easy and it's quite straightforward, provided that you know your pattern, either 5-spot, direct line, or staggered line drive. Okay, so this is all about areal sweep efficiency. Numerically, it is quite easier to estimate. And of course, lastly, we will talk about vertical sweep efficiency. Okay, because we want to know our recovery factor. It is displacement efficiency multiplied by areal sweep efficiency and vertical sweep efficiency. Okay, vertical sweep efficiency is defined as the fraction of the vertical section. So it is about a vertical section of the pay zone that is swept by the injection fluid. All right. The vertical sweep efficiency depends basically on mobility ratio again. So mobility ratio is really, really important for our water flood, and also volume injected and vertical permeability variation. All right. So again, heterogeneity, in this case, vertical heterogeneity is really important for our water flood performance. Okay. Of course, this kind of displacement that we desire from our water flood, piston-like displacement. Okay, that's the normal, the ideal story. But most of the time, that's not the way it turns. Okay, most reservoirs are stratified, vertically heterogeneous to some degree. So finally, you will get this kind of performance because of vertical heterogeneity. And of course, this this interval or this level actually the highest permeability layer, because your water move at the faster rate at this layer. Okay, our reservoirs are normally stratified or layered. There are a lot of high permeability streaks, fast zones, thief zones, fractures, and so on and so forth. Okay, and which will give us problems like, again, early water breakthrough, water recycling, which ultimately will give us poor sweep efficiency or poor vertical sweep efficiency. And what actually water recycling is? It is actually like this one, water recycling. So basically, you don't really push or displace your oil efficiently. Finally, you will just do water recycling. So you inject your water, and then your water moves in the reservoir. It will be produced at your producer. And again, you will process your water and inject the water back into your injectors. And basically, you just recycle your water. Okay. And of course, there will be a lot of bypassed oils. Okay. There will be a lot of bypassed oil zones because of this inefficient operation. And that's we don't want, of course. Right? So how we actually calculate or estimate our vertical sweep efficiency? There are a lot of approaches. We can do Stiles method, okay, provided that you know your permeability trend within your well, within your each well. And also you need to also do the extra Parson coefficient or the extra Parson analysis to obtain this V parameter, which will represent your heterogeneity. Okay, so if you have your log data, you calculate the extra Parson coefficient for each well using this formula. Okay, and using that information, V and also mobility ratio, you can use this plot, or you can also use this equation to finally calculate your vertical sweep efficiency. Because again, as a petroleum engineer or as a reservoir engineer, you need to actually estimate your recovery factor. All right, so this is easy. Provided that you know your mobility ratio, you just need to do analysis in laboratory to estimate the mobility ratio, and you need to also do reservoir characterization to obtain your V or the extra Parson coefficient to represent your heterogeneity. And you need to use this tool, either the plot or this equation. Okay, you can read it, the material in the textbook. Okay, it is in the literature. And if you have the phi or the extra portion coefficient from each well, you can create heterogeneity map. Okay, you can do kriging or you can do extrapolation to construct heterogeneity map, which will give you insight of how heterogeneous your reservoir is. Okay, so if you have, I'm sorry, it's typo. So if you have V equals to 0, it means that you are completely homogeneous. Okay, your reservoir is completely homogeneous. But if you have V equals to 1 or approaching 1, it means that you have heterogeneous reservoir. And that's very important to give you the insight of how challenging your water flood will be. Okay, like this one, I have several wells. I analyze them, I calculate the extra Parson coefficient, and I create the map, and I obtain this one. So it means that my reservoir is really heterogeneous, which means if I implement pattern water flood, it will be very challenging and it might result in not really good water flood performance. Okay, so in this way, I know I need to actually implement irregular water flood rather than regular pattern water flood. Okay, so actually after you know displacement efficiency, areal sweep efficiency, and vertical sweep efficiency, you can calculate your recovery factor provided by the water flood. All right, at last section, I will talk about water flood surveillance or water flood diagnostics or water flood performance analysis. It is really important and interesting topic. So as a student, you can also do research about the usage or the application of each surveillance tools. You can do water flood surveillance at field scale, sector scale, pattern scale, and well scale. And you actually need to do surveillance at all of these scales. There are a lot of surveillance tools: production plot, bubble map, and decline curve analysis, hull plot, churn plot, voidage replacement ratio, tracer, streamline, ABC plot, interference stance, interference test, I mean, saturation log, production log, and so on and so forth. And we will discuss only a few tools in this presentation. The first one is, of course, production plot, vintage plot. And of course, it is the simplest tool that we can do, but it is really actually very important. So we create a plot. Okay, it's a composite plot. Within this plot, we create a production plot, oil production plot, liquid production plot, reservoir pressure, injection rate, water cut, and many parameters we can plot actually within one plot. And with it will give us, it will tells us a story regarding our field performance, also our water flood performance. So like this one, at number 1, it means production started. Okay, very easy first. And then at number 2, we can see, okay, at number 2, production wrap up and peak. Okay, as a new engineer, you need to construct this kind of plot. And at number 3, reservoir pressure rapidly decline. Okay, actually, it is plotted at logarithmic scale. In linear scale, you will see the reservoir pressure decline. It's very rapid. Okay, and that's bad. We need to actually implement water flood or water injection as soon as possible. Okay, and that's why at number 4, at around July or May 2009, we implement water injection or water flood. Actually, we are quite late. Okay, because the reservoir pressure has actually rapidly declined. Okay, but so we are quite late, but it's okay because finally we implement the water flood. And then at number 5, we increase the injection rate. Okay, which will result in number 6, increase in liquid and oil production following the injection ramp up. Okay, so it means that our reservoir respond positively with our injection, and that's a good thing. All right, so there is a really strong correlation between production and injection, and that's a good news for engineers. Okay, and but now at number 7, we see at the history water injection rate decrease. Okay, at number 7, water injection rate decrease, which was followed by liquid and oil production decrease as well. The black line is the liquid production. The green line is the oil production. Okay, so again, it is a positive response. If you increase your injection, production will increase. If you decrease your injection, production also will decrease. Okay, and at number 8, fast water in fast water cut increase following water injection rate ramp up. At this one, at number 8, the water cut increased rapidly. So actually, what we did in number 5, maybe it will give us higher production for a while, but at the same time, unfortunately, the water cut increased rapidly as well due to the ramp up in the injection rate. So we need to be careful there. Of course, if you increase your injection, it will give you higher production. But what about the water cut? Water cut is our enemy actually. We don't want it to increase rapidly. Okay, so this is the problem here. So water cut increase rapidly at number 8. And at number 5, at number 9, we can see reservoir pressure steadily increase. Okay, so it is a steady increase of our reservoir pressure. So after it declines, it depletes rapidly, we can slowly but at stable rate, we can increase our reservoir pressure. Right, so this kind of analysis, this kind of surveillance analysis you actually need to do as a reservoir engineer, petroleum engineer, field engineer. Okay, and yeah, that's actually the arrows for each history. And you can also plot this one, rate versus cumulative oil plot. I plot it. You can use Excel, or in this particular case I use OFM. Okay, you plot it this way: oil rate versus cumulative oil production. You just need to find a linear trend, and you do matching there and extrapolation there. If you have gentle slope, like at this interval, it means that you will have higher recovery factor. You have higher sweep efficiency. But if you have steep slope, you will have lower recovery factor. That's simple, right? So actually, there is a treatment, there is an intervention that finally change the slope of this plot. And we need to actually know in our production history what really happened around this time, so that the slope changed significantly from previously steep slope to more gentle slope. Okay, so as you can see from this plot, something happened around this time which finally improved the sweep efficiency, so that the production will give us gentle slope. Okay, so one plot is very important, but it is actually very easy to construct. You can also construct recovery factor versus hydrocarbon pore volume injected. It's also quite easy, provided that you know your hydrocarbon pore volume and provided that you know the cumulative water injection. Okay, as a reservoir, you need to construct a lot of tools, construct a lot of analysis, and this is actually very important, very popular for water flood analysis. So in vertical axis, recovery factor; in horizontal axis, hydrocarbon for volume injected. First, we will start in primary recovery period, so there is no pore volume injected. That's why this pore volume injected is of course 0 within our primary recovery period. And after the injection, it will move like this one. Steep slope means higher sweep efficiency. and higher recovery factor. But some things happen within this time that change the slope. Maybe water breakthrough, maybe water recycling, we don't know. We need to actually go back and read our production history, operation history to know what really happened. Around this time, they change the slope, that change the sweep efficiency. Okay, finally, it, it follows this poor efficiency line. Unfortunately, it will give you lower sweep efficiency and of course lower recovery factor. Again, you can construct also water oil ratio against cumulative oil production plot. All right. This is the plot, but analytically you can also construct by using this equation. Okay, it's actually a linear relationship, a linear correlation. In this plot, gentle slope means your operation is giving you higher sweep efficiency, higher recovery factor. But steep slope, it will give you lower sweep efficiency and lower recovery factor. So actually, previously, we follow a green line with gentle slope. But something happened around this time that will give you steep slope. Okay, finally, you can see if you forecast the period with gentle slope, if you forecast to the cut-off water oil ratio, and you can see you can actually obtain cumulative oil production more than 100,000. Okay, but something happened here: inefficient operation, inefficient water flood, water breakthrough, or water recycling, and it will give you only around this number, below 100,000 million barrels of oil. And the difference is huge. All right, so it means that water recycling, water breakthrough is really an enemy for water flood performance. And using this plot, you can actually analyze the efficiency. And if you see this kind of plot, as an engineer, you need to do intervention. You need to prepare what actually can we do to 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 keep our production following this gentle slope. Maybe finally you need to do enhanced oil recovery to obtain higher sweep efficiency. Or maybe you just need to do infill drilling. You just need to do water flood optimization, pattern balancing, pattern realignment, or maybe you need to do stimulation to keep your sweep efficiency. Again, you can also construct churn plot. Okay, so this is the WOR and the derivative of your water oil ratio plotted against time. If you have this trend, it means that you suffer water coning problem. All right. So if your water oil ratio increase and then it is turned to be quite steady at the end of the production and the derivative curve decrease, it means that you have water coning. But if your water oil ratio and the derivative increase with constant slope like this one, it means that you have multi-layer channeling. You need to do this analysis for each well. In my case, I've done the analysis for all my wells so that I know the problem for each of my well, whether it is water coning or it is water channeling. And I can do intervention to maybe slower down the water coning to make it stable, or maybe I can shut my well to stop this water channeling problem. All right. And of course, it is very interactive, very uh, really interesting surveillance tools. Bubble map. Okay, this is the map. We have producers and we have injectors. And of course, we want to know the drainage area, the production drainage area, and also the injected area. And that's why we construct bubble map. We can actually estimate ideally our injection radius, our injection area using this equation. Okay, it's easy actually. This one is actually the injection efficiency, around 50%. to 70% to to give us to allow some losses. All right, and this is the cumulative injection, thickness, porosity, average water saturation at breakthrough, and initial water saturation. You can estimate it and you can construct your bubble map easily. Okay, so it is really, really useful. It tells us a lot of information like this one. It tells you the flood front, where the flood front is. It tells you the overflooded area, like this one. It is overflooded. You have two injectors at very close position, and this area is overflooded. And in this area, you suffer water breakthrough. The waterfront actually arrives at your producer. So in this spot, you suffer water breakthrough already. And in this spot, you suffer water recycling because your production area is within the injection area of this injector. All right. So this is one of the thing that bubble map can tells us. And but it can also give us where we can actually locate our infill drilling well. Like this one. We can actually locate our infill drilling area here in this spot. Okay. It is supported by injector, but with no oil well. So it means I can put my infill drilling well at this location. Okay, so this is the analysis bubble map can give us. So it is very interesting, very, very useful to construct. And also voidage replacement ratio. It is material balance analysis. Okay, it's quite easy. VRR, or the voidage replacement ratio, we can calculate it by using this formula: actual injection rate divided by the actual total production rate. We know the water injection rate. We know the production rate for each phase: oil, water, and gas. We need to keep our VRR around 1 to 1.2. Okay, of course, finally the best number is 1. It means that the injection and the production are balanced. But to compensate for injection losses, we can inject more water and to achieve VRR equals to 1.2. If your VRR is below 1, it means that your pressure will fall, okay? Because you produce more than what you inject, VRR below 0. But if your VRR is high, well above 1, it will give you risk of fracturing. Why? Because you inject more than what you actually produce. It will pressurize your reservoir fast, and it turns out to be fracturing phenomena. And we don't want that because it will complicate our injection profile. All right. And yeah, it is the last some yeah, actually. Next, we discuss about hull plot. Is also very important for analyzing the injectivity for each of our injector. We plot it this way. It is derived from injection analysis using Darcy flow, uh, assuming a radial or pseudo steady state flow regime. Okay, if you follow this trend, it means that you have normal injection. Your injectivity is constant. If you follow this trend, the plot giving you this trend, it means that there is an abrupt stimulation. Maybe there is a fracturing, or maybe you do acidizing, and of course the slope will be decreased. And if you have this trend, it means that you experience gradual stimulation, but most of the time your hull plot will give this trend, either abrupt damage or gradual damage. So the injectivity will drop, maybe because of low quality oil, in low quality water injected into your injectors, maybe dirty water, due to solids, due to oil in water content, and of course, you will suffer formation damage or injectivity impairment. That's what actually hull plot can tells you. Okay, either you have sustained injectivity, higher injectivity, or decreased injectivity. Okay, we actually can construct by deriving this equation to finally obtain the equation for the slope. All right, so this line, it has a slope, and the slope can be numerically calculated using this equation. So finally, the slope is influenced by viscosity, the reservoir radius, well radius, permeability, thickness, and of course, skin. All right, so if you have higher skin, of course, you will have higher slope. And that's why this gradual damage, higher slope, it means that you have higher skin. Okay, but if you stimulate your well, stimulate your injector, S will decrease, and of course the slope of the hull plot will decrease as well. You need to construct hull plot for all your injectors, like this one. Each injector you create the hull plot and you see which wells need stimulation, which well can run normally. Okay, like this one. Some wells show an increased slope, which tells me, oh, I need to do stimulation in this particular injector. Maybe I can frac the well. Maybe I can do azidizing for each well. You can also combine all hull plots to see which well lies within the higher resistance to flow and which well give you higher performance. All right. So this is an analytical tool to tell us which injector is the best and which are the injectors are poor. Also, you can construct heterogeneity index plot. All right, it is a quadrant analysis. There are 4 quadrants. You plot the heterogeneity index for each well, and you can know which well will be in quadrant 1, which means higher productivity, high oil, high water. Which well goes to good oil quadrant? High oil with low water. This is the best quadrant. And you can know right away using this analysis, using your software maybe, or you can also construct your spreadsheet to construct heterogeneity index analysis. You can know which wells are within this quadrant 2, which are the best well for you. But quadrant 3 and quadrant 4 are quite problematic. Quadrant 3 gives you low productivity wells, low oil, and low water, which means that wells within this quadrant need stimulation. And lastly, bad water. The quadrant 4, low oil but high water. In this case, maybe you need to do water shut off, or maybe you can just shut in those wells, right? Because this is the well with poorest performance. And lastly, maybe the surveillance analysis, decline curve analysis, of course. You need to do decline curve analysis for each of your well and for your overall reservoir. Okay, this is easy, and this is also popular. Decline curve analysis can give you or can show you exponential profile, hyperbolic profile, or harmonic profile. This is actually the calculation, the formula to calculate the or to forecast the production rate. Q is production rate. B is exponential. Okay. And D is decline rate. You need to estimate your B and your D in order for you to can forecast the production. Wells working under water flooded reservoir, if the water flood performance is quite good, it can gives you B equals to zero point 0.5, which is shown also by water drive reservoir. Okay, so your performance will be more or less like water drive reservoir with B equals to 0.5. So like this one, if your B is 0, it means that maybe your water flood performance is not that good, right? Like this one, poor water flood performance gives you B equals to 0. But if your water flood performance is quite good, you can achieve this number, B equals to 0.5. All right. And you can construct your decline curve analysis like this one, construct using software. And you can tell from this profile, apparently this reservoir show us hyperbolic trend. And that's quite acceptable because this particular reservoir is water flooded. Okay, we do water flood for this reservoir. Okay, so finally you need to do decline curve analysis for each well and for your entire reservoir. Okay, please be careful because decline curve analysis is quite subjective. Of course, you can see exponential trend like this one or this one, a lot of apparently exponential trend, but you need to actually look at the whole profile, okay, to finally say that it is hyperbolic performance, right? And of course, you can see if we forecast this interval exponentially, of course, it will give you lower reserve, lower ultimate recovery. Okay, but because you provide water flood for your production, you can achieve lower decline rate and hyperbolic trend, which will finally give us higher estimate recovery. And you can also use, lastly, empirical method for analyzing or for estimating your recovery factor. All right, this is the quick look analysis, whether you can use Guthrie and Greenberger method. If you know permeability, Conant water saturation, oil viscosity, porosity, thickness, then right away, you can easily calculate your recovery factor. Or you can also use your ARPS method, provided that you know the porosity, formation volume factor, initial water saturation, the viscosity ratio, permeability, pressure, and abundant pressure, then you can easily calculate or estimate your recovery factor. This is a quick look method. Finally, of course, you need to also calculate the displacement efficiency, sweep efficiency, vertical sweep efficiency, right? Compare with this analysis. All right, I think that's all from my part. I give back the time to the moderator. Thank you so much.